What is up, everybody? It is Mr. Holtz, and today we're going to be going through some practice problems for stoichiometry, where we'll get some practice going through balancing reactions, calculating limiting and excess reactants, and theoretical yields. Okay, so if you need some practice with stoichiometry or doing some kind of calculations, how much product you get from a certain amount of reactant, these should be some great practice problems to go through. So the first one we're going to take a look at is right here for us. And it says aluminum chloride solid and molecular bromine are produced through the unbalanced reaction above. Okay, notice that it's unbalanced, so we're going to have to balance this. A chemist reacts 130.20 grams of aluminum bromide, which is our first reactant, with 130.20 grams of chlorine gas. So both reactants have the same amount of substance, but that doesn't mean they're all going to be both used up. We're still going to have a limiting and an excess because that's what we're solving here. But before we get to that, we need to balance the reaction. So if you have seen the video on my YouTube of how I balance them, you'll notice that the way I do it, and it's kind of hard because this paragraph is in the way, but I record how many of each atom I have on both the left and the right for every kind of element that's in this equation. So I have aluminum, I have bromine, and I have chlorine. And that's about it. So, make a little table here. We start with one aluminum on the left and one on the right. So these prefixes should probably be the same, right? That's the only place we're going to have aluminum. We have 2 chlorines on the left, 3 chlorines on the right, 2 bromines on the right, and 3 chlorines on the left. So this one's actually not too bad. Anytime you have subscripts of 2s and 3s that are being thrown back and forth, those are usually going to be helpful to try as our coefficients. So what we end up getting here is coefficients of 2, 3, 2, 3, 2, 3, 2, 3. So we have 6 chlorines here, okay? 6 chlorines on the other side, right? 2 times 3. 2 aluminums, 6 bromines on the left, and 6 bromines on the right. Awesome, so our equation is balanced now. So let's get to the actual stoichiometry part. Now, when we're determining the limiting and excess reactants, the easiest way that I think to do that is to solve for how much product do one thing specifically. In this case, it doesn't matter because we're not being asked for that, but in later problems, we'll figure that out. So in this case, we can just determine how much aluminum chloride, which is our first product here, how much of this is being produced, or how much of this would we produce if we only used 130.2 grams of aluminum bromide, assuming that the chlorine is excess. And then we're also going to have to do a second calculation where we figure out how much aluminum chloride, right, our second product here, how much of this would we get if we only used 130.2 grams of chlorine gas. And in this case, our aluminum bromide would be our excess, or there's so much of it left that we're not going to use all of it. So the way that we would solve for this is I would set up a stoichiometry for both of these things. So we know we're starting with 130.20 grams of both the aluminum bromide, so AlBr3. So that's going to set up our first stoichiometry, and we'll tackle that in a minute. We're also going to need to set up a second one because we also know we started this problem with 130.20 grams of our chlorine gas. And again, we'll do that later on. Now, what are we actually doing here in this stoichiometry? Well, you know you're producing aluminum chloride and you're producing bromine, so it doesn't really matter which one you're going to. But what we're going to do here is I'm going to figure out if I have this much aluminum bromide and I use 100% of it, okay, I use every single last gram, how much aluminum chloride will that give me? Then I'm going to do the same thing with our chlorine gas down here. If I use all 130.2 grams of chlorine gas, how much aluminum chloride would this give me? And then I'm going to compare them, okay? So we know we need to convert from grams to moles because we can't compare one substance, right? We're comparing our aluminum bromide to aluminum chloride, and we can't do that unless they have common units. Remember, the only way we can compare one substance to another substance is in units of moles. So we would have to convert our amount of aluminum bromide here to some amount of moles of aluminum bromide. So the way that I'm going to do that here is I know the molar mass, and you guys can either look this up or calculate it with a periodic table, but I know the molar mass of aluminum bromide is 266.69 grams. So that's how much aluminum bromide is in 1 mole of aluminum bromide. Because remember, aluminum bromide moles, or moles of anything, is based on how many molecules we have, right? Not what they're made of or how big they are or whatever, okay? Now, if we're going from aluminum bromide to aluminum chloride, I know I'm going to want to get rid of my aluminum bromide. The only way I'm able to do that is by canceling out with moles of aluminum bromide. And I want to switch to aluminum chloride. But the only way I can compare one substance to a completely different substance in chemistry, again, is with these moles. Now, this is why we needed our balanced equation, because this step right here in the middle is where most people get confused, because we need to correlate how many moles of aluminum bromide would I have to put into this balanced reaction, and how many moles of aluminum chloride would I get out of this balanced reaction. Conveniently here, both of these are 2. And in this case, you could end here, but most of the time we're going to want to convert our final substance to grams as well. So I'll do that just for fun. All right, 1 mole of aluminum chloride has a mass of 133.34 grams. And again, you guys can look this up, or you can find it on the periodic table if you add them all up yourself. Okay, so now let me just check to make sure I did everything correctly. Okay, I started with grams of aluminum bromide. I converted from grams to moles of aluminum bromide, so I know this unit I'm going to get rid of. Okay, here I converted from moles of aluminum bromide to moles of our product, which is moles of aluminum chloride. So I know both of these are going to cancel out as well. I'm just making sure I canceled all my units correctly. Now here I converted moles of aluminum chloride to grams by multiplying by the molar mass. So I'm getting rid of moles, which means our final answer here is going to be in some amount of grams of aluminum chloride. Now, if you actually do this calculation, you multiply everything across the top and then divide by everything that's on the bottom. So 130.2 divided by 266.69. These are going to cancel out, right, because they're both 2, times 133.34 gives us a value of 65.10 grams. Now, what does this actually mean? Well, this value tells us if you are doing this reaction right here, okay, this balanced reaction, and if we only added 130.20 grams of aluminum bromide and we have excess chlorine, meaning there's so much of it, it doesn't even matter how much because we're definitely going to run out of the aluminum bromide first, that means that if we use up all 130.2 grams of this substance, then we will produce 65.10 grams of aluminum chloride, okay? So now we need to figure out how much aluminum chloride would we produce from 130.2 grams of chlorine. And hopefully those are going to be 2 different numbers, but it's possible it could be the same. I've never actually run into a scenario where you get both answers that are the same, but sometimes you'll be given a problem where that happens on purpose. Okay, so we're going to do the same kind of process here. And since I'm starting from grams of something else, you can kind of follow your previous setup, okay? So I'm going to convert to moles, and I know that 1 mole of chlorine gas has a mass of 70.9 grams, because each chlorine atom is 35.45. Okay, so I've converted to moles here. Now, again, I need to convert from moles of our reactant to moles of our product. And again, the way that we do that is by using our balanced coefficients. So we would have a 3 for the coefficient of chlorine and a 2 for the coefficient of aluminum chloride. So 3 down below and 2 up top. Now, again, the last thing I'm going to do here is convert from moles of aluminum chloride to grams of aluminum chloride. I know the molar mass is still the same, 133.34. So I can go back and make sure I canceled out all my units correctly, which I'm pretty sure I did. Grams of chlorine gas cancel out with grams of chlorine gas. Moles of chlorine gas cancel out with moles of chlorine gas. Moles of aluminum chloride cancel out with moles of aluminum chloride. And again, if you do this multiplication and division all the way across, you will get a production value of 163.24 grams of aluminum chloride. Okay, now this value here means if you used all 130.2 grams of chlorine gas in this reaction, and you had nearly unlimited aluminum bromide, meaning at no point would it hold you back until you ran out of chlorine gas, using up all of this chlorine gas would produce 163.24 grams of aluminum chloride. However, from the amount of aluminum bromide, we know we can only get 65 grams of aluminum chloride, okay, or a little bit over 65 grams, which means that there's no way we're actually going to be able to produce this much, because by the time we get to 65 grams of this aluminum chloride being produced, that tells us we've already used up all of our aluminum bromide. So anytime you're doing a calculation like this, where you start with how much of our reactant 1 are we using and how much of reactant 2 are we using, you're going to end up with values like this. Generally, they will be different, but the smaller value is always going to be the limiting reactant, because that tells you this substance ran out first, okay? Obviously, if we didn't run out of aluminum bromide, we would eventually make 163 grams of aluminum chloride. But that tells us that there's some chlorine left over that's not being used, because by the time we get to 65 grams, all of our aluminum bromide is already used up, okay? Which means that our limiting reactant is whatever produces the least amount of product, which in this case is our aluminum bromide. Okay, so there is our answer for part 2. And we have now solved this problem. We balanced the reaction. We determined the limiting and excess. So let me write in the last one. That means that our excess reactant would be our second reactant, or our chlorine gas, okay? Because there's more of this left over when the reaction is done. That means it's in excess. Okay, moving on to problem number 2. So here again, we are given an unbalanced equation. In this case, it's a combustion reaction. So the problem says, the unbalanced reaction given above is the combustion of butane gas, and butane is this molecule C4H10. That's what you find in the little Bic plastic lighters. Using a butane lighter, you collect 7.31 grams of water vapor. So the first thing we're going to need to do is balance the reaction. I already did this, so if you guys need some help, there's another video on my YouTube channel of how to do that with some practice problems. But feel free to pause this and do it on your own. The coefficients I got were 2, 13, 8, and 10. Okay? So we balanced the reaction. That's great. If you guys need help with that, there should be more support on my YouTube channel if you need it. If you want more than what's already on there, then comment down below and let me know that you guys need some more practice, and I'm happy to make that for you. Okay? So again, let's see. We balanced the reaction. Part 2. How many moles of water vapor were you able to collect? Well, this should actually be pretty easy, because it told us that we collected 7.31 grams of water vapor. So now it's asking, how many moles of water vapor did we collect? So this should be pretty simple. And again, the way that we do that, all we're doing here is really converting grams to moles, and we're starting with this value. So they said that we collected 7.31 grams of water vapor. Now water, it doesn't really matter what phase it's in. It could be solid, liquid, or gas. This is the same amount, right? Because it's based on mass. Now, to convert from grams to moles, just like we did up top, we're going to divide by the molar mass. The molar mass of water is 18.02 grams, right? 2 hydrogens and 1 oxygen. So 1 mole of H2O is equal to 18.02 grams of H2O. Now this is a pretty simple division. All you have to do is divide 7.31 by 18.02. And what you end up getting from that is 0.406 moles of H2O. Okay, awesome. This is the amount of moles. So we have just solved for question number 2. Great. The next question says, determine the amount in grams of butane gas that must have been combusted to produce the collected water vapor. Assume 100% yield. Okay, this is important because if this was not 100% yield, then it would be really hard to calculate how much butane this actually came from. Okay, so what we're actually going to be doing here is we're going to go backwards from what we did in problem 1, and we're going to start with moles of product and work backwards to see how much reactant must we have used instead of what we did earlier, which was how much product can I get from this amount of reactant. Okay, so let's take a look at how we do that. Again, we're starting with 0.406 moles of H2O. But what we want to know is how many grams of butane, there we go, or how many grams of this C4H10 did we actually have to use to get 0.406 moles of water? Well, just like always, I'm going from one substance, right? I'm starting with water, and eventually I'm going to end up at C4H10, which is why we needed our balanced equation. So down here, what I'm going to do is, because we're already in moles of water, I'm going to convert from moles of H2O to moles of, instead of our product in this case, because we're starting with our product, I'm switching to moles of our reactant, which would be our C4H10, right? That's our butane gas that we're actually combusting here. Now, I'm going to put numbers in here based on our coefficients. So our coefficient for water is 10, and our coefficient for butane here is 2. Okay, awesome. Now, keep in mind, this problem said determine the amount in grams. So it's important to not end at moles. We want to convert to grams. So 1 mole of C4H10. And again, you guys can find this on the periodic table. How many grams of C4H10 are there? Well, if you add up 4 times 12.01, which is carbon, and 10 times 1.01, which is hydrogen, you'll get an overall molar mass of 58.12 grams. So that is the molar mass of butane. And that ends us with grams of butane, which is awesome. Now, did I do this correctly? Well, moles of water are going to cancel out with moles of water. Moles of butane are going to cancel out with moles of butane, so the only thing I'm left with is grams, which is perfect. And again, if you do this multiplication across and divide by that last 10 down there, you should get about 4.72 grams of butane. So this is actually our answer. And what this tells us is if our reaction was 100% perfect, which they're not really going to be, but on paper, that's okay. If this reaction was 100% perfect, then it would require exactly 4.72 grams of butane gas to produce 0.406 moles or 7.31 grams of water, okay? Because these two amounts are the same thing, right? We're just expressing them with different units. But what this tells us is if you perfectly combust 4.72 grams of butane with, keep in mind, oxygen is in here, but if it's in the atmosphere, we can assume oxygen is excess because it's 20% of the gas around us. We would get 7.31 grams of water from that reaction if it was perfect, right? If we had 100% yield, okay? Now, in the next problem, we're not going to have 100% yield, but that's okay. All right, moving on. We got one more problem to go through here, problem number 3. Now, this reaction is actually super cool. So what the problem here says is the unbalanced reaction above is known as the Haber process, which is the main industrial procedure for the production of ammonia. Now, ammonia gas is NH3. It's used in fertilizers and all kinds of other things. It's used in cleaning materials. So it's very widely produced all around the world. So what it tells us is 79.76 liters of hydrogen gas, which is our first reactant here, is reacted with 42.03 grams of nitrogen gas, which is our second reactant here. So we have to balance the reaction, determine the limiting reactant, determine the theoretical yield in grams of ammonia that is produced. So how much ammonia do we think we're actually going to produce? And determine the amount in grams of excess reactant left over. So depending on which one of these reactants is excess, we need to calculate how much of it is left, because excess means that we didn't use all of it. So we're going to calculate how much we didn't use. And then we're going to calculate percent yield if we were actually able to collect 40.44 grams of ammonia. Now, we can't do that until we determine the theoretical yield, and we can't do that until we balance the reaction. So let's go ahead and do that. Now, this one's pretty simple since they're all subscripts of 1, 2, or 3, and there's only 3 things here. Again, feel free to pause the video and go through it on your own, but there's only nitrogen and hydrogen in this reaction. So the coefficients we get to balance it are 3, 1, and 2. 6 hydrogens, 2 times 3, 6 hydrogens, 2 nitrogens, 2 nitrogens. That's it. All right. So what is our limiting and excess reactant? Well, we know that we're starting with 42.03 grams of nitrogen gas, which is our N2. Okay, so I'll set up our stoichiometry for part 1. And we also know, and this is a little bit different here, that we start with 79.76 liters, 79.76 liters of hydrogen gas. Okay, make sure that's right. Okay, cool. So set up our second stoichiometry here. Okay, the top one's easier because we've already started with this. We've done this before. So again, we're going to convert from grams to moles because we can't compare moles of one thing to, or we can't compare grams of one substance to another. So if you calculate it out, 1 mole of N2 has a molar mass of 28.02 grams. All right. Now, we're converting from moles of nitrogen, which is our reactant here, okay, moles of nitrogen, and we want to figure out the theoretical yield. So in this problem, we're actually going to solve for part B and part C at the same time, okay? So moles of nitrogen to moles of ammonia, right? This is our only product, so we don't even have another option of things to look at or things to calculate too. So moles of NH3. And again, eventually we're going to want our theoretical yield in grams. So I'm going to make sure I convert this all the way to grams. But what are our coefficients here? Well, we have 1 mole of nitrogen gas to 2 moles of ammonia. Okay. Now the last thing we need to do here is multiply by the molar mass. So 1 mole of NH3 has a mass of 17.04 grams of NH3. Awesome. So if you go through and you solve this by multiplying and dividing, we know our grams are going to cancel out, moles of nitrogen are going to cancel out, moles of ammonia are going to cancel out, and we are left with grams of ammonia. So if you do the actual calculation, you should end up with about 40.5, give or take how you rounded, 40.5 grams of ammonia. Okay, cool. We have one value. Now, we don't know what's our limiting and excess yet because we haven't calculated the second one, but this one's a little bit trickier. Now, in our class, we haven't gone over this yet, but one thing that we're going to find when we're dealing with gases, especially gases at something called STP, which really means standard temperature and pressure, standard temperature and pressure, which really just means 1 atmosphere, okay, and for pressure. So pressure equals 1 atmosphere and temperature equals 0 degrees Celsius. Okay, now we'll talk more about this in class, but the only thing you guys need to know is that at STP, 1 mole of gas, and it doesn't matter what it is, it could be hydrogen gas, it could be nitrogen gas, it could be oxygen gas, it could be chlorine gas. 1 mole of gas equals 22.4 liters. And what that really means is at standard temperature and pressure, at 1 atmosphere and 0 degrees Celsius, 1 mole of gas takes up 22.4 liters of space. Okay, that's how much volume it requires to match this pressure and temperature. All right. So the conversion that we need here is we know that 22.4 liters of H2 gas is equivalent to 1 mole of H2 gas. Now, this problem didn't tell us that we're at standard temperature and pressure. It didn't say STP anywhere, but it's safe to assume that you're at STP if they give you liters and nothing else, because if you're not at STP, this would be kind of hard to calculate. Okay, so now again, we're going from moles of H2 to grams of ammonia eventually. So we're going to need to cancel out moles of H2. That's how we can convert to moles of ammonia. So what are our coefficients here? We have a 3 for the hydrogen gas, okay, 3 moles of hydrogen gas, and 2 moles of ammonia. All right, just like in this problem up above, we know that 17.04 grams of ammonia is the same thing as 1 mole of ammonia. So how are we doing here? Well, we're canceling out liters of hydrogen gas with liters of hydrogen gas, moles of hydrogen with moles of hydrogen, and moles of ammonia with moles of ammonia. So when you calculate this out, what do we finally get? Because we know that we're ending up in grams of ammonia, which is exactly what we're looking for. And we end up calculating for, hold on, I think I wrote those backwards. So congratulations to you if you know that I did this calculation wrong. On my paper that I have, I wrote them in the opposite directions. So this is actually where our 40.45 is supposed to go. That came from our liters of hydrogen gas. So I apologize if you caught me on that and I didn't catch it until now. But here we go. So let me erase this really quick. This is actually not 40.5. So good for you if you did this correctly. This should be 51.12 grams of NH3. Okay, so I did these backwards when I did it on paper. I did the liters of hydrogen first and the grams second. So they were switched, but these should be correct now. Okay, and just like in problem number 1, we know that anytime we're given a smaller amount of product, this is our limiting reactant, okay? Because it limits how much ammonia we can make. All right, this would be our excess. So we should have some of this left over. Since this is our nitrogen gas, we know that the excess is our N2, and we know that the limiting reactant is our H2, which means that this 40.45 is what we would call our theoretical yield. Okay, theoretical yield. And the reason for that is because if our reaction is 100% perfect, we are going to use all 79.76 liters of hydrogen gas to produce 40.45 grams of ammonia. And when we get there, we stop because there's no more hydrogen gas left, which means there's some nitrogen left over that we didn't actually use. So part D here says to determine the amount in grams of the excess reactant that is left over. So since we know our excess reactant is nitrogen, how then do we figure out how much of our nitrogen is left? Because if it's excess and we know we didn't use it all, there must be some left over. So the way that there's a couple different ways that you can do this, but I think the easy way to do this is we already know our theoretical yield, which is the amount that we get from our limiting reactant. So let's say that if this reaction works 100% perfectly, we will get 40.45 grams of ammonia. Why do we know that? Because that's the theoretical yield that came from our limiting reactant. Okay, so just like we did up above in this example right here, we calculated how much butane gas was actually needed to make the amount of water we collected. So now I'm going to do a similar process, okay? If our theoretical yield is 40.45 grams of ammonia, then I can work stoichiometry backwards to figure out how much, since our excess reactant is nitrogen, how much nitrogen was required to actually produce this much. And then I can subtract that from how much we started with, okay? So again, just like we used up before, but now we need to divide instead of multiply. The molar mass of ammonia is 17.04 grams. So that's the same thing as 1 mole. We know that we need moles to convert from one substance to another. So moles of NH3 to moles of, again, our excess here is N2. So what are our coefficients? 2 for ammonia, 1 for nitrogen. So 2 and 1. And here, because it's asking us what is the excess in grams, we need to convert to grams. So 1 mole of N2 is the same thing as 28.02 grams of N2. So what we end up getting from this, and be careful what you actually use these numbers for, what we end up getting is 33.26 grams of, not NH3, sorry, right, N2, because we're calculating how much reactant did we actually need for this, okay? So if we wanted to make 40.45 grams of ammonia, based on our balanced equation that we have up above, we know, based on this calculation, that it would require 33.26 grams of nitrogen gas if it was 100% perfect. Now, that's not really what the question is asking us. It's asking us how much of that excess reactant do we have left. So how much did we start with? We started with 42.03 grams. So 42.03 grams of nitrogen. And the reason I'm using these differently is because this is what we started with. This is what we used. So if we subtract what we used from what we started with, we should be able to calculate how much is left over. Okay? So if you do this actual subtraction, you should get about 8.77 grams of N2. And this value represents how much nitrogen gas is in excess. Okay? That means as soon as we produce 40.45 grams of ammonia, we have completely run out of hydrogen. And at this point, there's exactly 8.77 grams of nitrogen left. So that's how much does not get used in this reaction. Now, we're not done yet. We have one more thing to do. It says if 40.44 grams of ammonia is collected, calculate the percent yield of this reaction. So how do we calculate percent yield? Well, percent yield is, let me see if I can do this in a different color here. I'll just keep using this blue. Keep in mind that percent yield, the way that we calculate that is we take our actual, or whatever we end up actually collecting, our actual yield, which in this case, well, we'll get there, divided by our theoretical yield, or what we expect to collect. And then because we want this as a percentage, we don't leave it as a decimal like this. We multiply by 100 because that's what gives us a percentage. So in this problem, if we actually wanted to plug things in, the actual yield is what we're given up here. Okay, it says if 40.44 grams of ammonia is collected, so if that's the amount that's collected, that's our actual yield. Okay, so 40.44 grams is our actual yield. Now, based on our stoichiometry earlier, we know that our theoretical yield is right here, 40.45. So they're not exactly the same, but they're pretty close, which means we collected almost all of it, but not exactly. Okay, again, multiply by 100. Now, this is going to be pretty close to 100 because we collected almost all of it, but we missed about 0.01 grams of that substance. So if you do that calculation and you multiply by 100, you'll get about 99.98%. So that is our percent yield for part, I think that's part E. Good, part E. So it says calculate the percent yield. We did that right here. So our percent yield is 99.98%. Awesome. So hopefully that was helpful. I know we went through quite a bit of different kinds of problems. So hopefully that was helpful in terms of finding, limiting, and excess reactant, calculating percent yield, and just in general helped you understand what does it actually mean when we're converting from one substance to another, doing this kind of stoichiometry. So as you guys will find, as you go through more problems, you can do this a lot of different ways, and you can plug certain things in to find a calculated value with more than one process, but they should still give you the same answer, okay? So Hopefully you guys liked this. Hopefully it was helpful. Make sure you guys hit that like and subscribe button and comment down below with what you guys would either like more help with or if you like this video. Thanks so much. I'll see you guys later.